So up until this point, we've been verifying that a given function is a solution to a differential equation, and we've been finding particular solutions, but we haven't actually been solving them ourselves. And so that's our goal for today, to be able to solve these differential equations on our own. And I had mentioned in the previous video that we've actually already been doing this for a good portion of the year. All right, so let's start with example 1, and hopefully you'll see what I mean. All right, so we've got a differential equation here, right? We have y prime equal to 6x, right? And it's a differential equation because it involves a function and or its derivative, in this case just its derivative. And let's think about what this is actually saying. This is saying the derivative of y is equal to 6x. I bet you could very easily come up with function y, right? If you are told that the derivative of y is 6x, what would you possibly do to figure out what function y is? Hopefully you're thinking integrate, and that would be exactly it, right? If y prime is 6x, then function y must be the integral of 6x. So let's do that, right? Well, that's going to integrate to 6x squared over 2 plus c, of course, always plus c, which just gives us 3x squared plus c. Fantastic. There's your solution to the differential equation, right? Y equals 3x squared plus c. That function will satisfy the differential equation in example 1. Done. Let's move on to example 2. Don't worry, this is going to get a little bit more interesting, I promise, but we're just going to lay the groundwork. Okay, in example 2, we're given dy dx equals secant squared x. Again, just a different way of saying that the derivative of y is secant squared. So we think, all right, well, if the derivative of y is secant squared, then y must be equal to the antiderivative of secant squared x. And then we start thinking, whose derivative is secant squared? And that would be tangent of x plus c, of course. Hooray, we found the solution to the differential equation. The function y equals tan x plus some constant will satisfy the differential equation in example 2. This is cake, huh? Example 3. Solve the differential equation. Okay, some business here. All right, well, now this isn't as clear-cut as perhaps what we were looking at in examples 1 and 2, where we were just flat out told, oh, the derivative of our function is this. But the derivative of our function is there, right? And maybe you sort of already have a feeling about what we should be doing at this point. While we don't have a flat out y prime equals, we're not very far from that, right? With just a little bit of algebra, we can very easily obtain y prime equal to 5x over the square root of 3 minus x squared. Great. All right, and so now we have the derivative, right? Y prime equal to all this stuff on the right. And unfortunately, it's not so simple as just looking at the derivative and saying, oh, well, then the antiderivative is this. This is going to require a little bit of work. So this will just be a nice little refresher on some of our integration techniques. And if you're thinking u sub, you would be correct. Because notice I see a function in here, right? This 3 minus x squared, and something to the tune of its derivative up here, right? At least x is of the right order to be the derivative of x squared. So we'll go with that, all right? So before we get too far ahead of ourselves, we're pretty much just saying if the derivative of our function is 5x over root 3 minus x squared, then function y will be the antiderivative of the expression on the right. Okay, here we go, dx, and let's do our u sub. All right, so a good choice for you would probably be 3 minus x squared. Then let's go ahead, get du dx, which would be negative 2x, and let's start rewriting. Okay, so instead of writing root 3 minus x squared in the bottom, I will just write root u. Okay, and now I need a substitution here. Let's see, I don't think I'm going to end up eliminating the 5 anyhow. I'll just write that in. All right, and now we need something that is equivalent to x dx, because everybody else has been accounted for. All right, so I'm looking for something that's exactly equal to x dx, and that's going to come from here. All right, so we'll do du equal to negative 2x dx, and then a little bit more algebra, we get that du over negative 2 is exactly equal to x dx. So this is what I can swap in for x dx in my integral. Alrighty, so we'll write du over negative 2, and then we'll simplify this thing. All right, so we'll pull out a negative 5/2, and then we're left with du over root u in the integrand, which is really just negative 5/2 times u to the negative 1/2 du. So we'll just do reverse power rule on this, and we'll get negative 5/2, right? U to the positive 1/2 divided by 1/2, so that's actually going to be times 2 over 1, right? And then, of course, plus c. And when we simplify this, we're going to get, well, these 2's will cancel. We'll get negative 5, u to the 1/2, that's just root u, plus c. And so then when we back substitute our expression for u in terms of x, we'll get negative 5 root u was 3 minus x squared plus c. All right, so that was a little bit more work. But again, all we did was solve by integrating. And so this general solution here would be function y, which would satisfy the differential equation as it was given above. Okay, good. All right, one more example. Example 4. Solve the differential equation y prime, right, is equal to negative x squared over 3y. So this is nice. They flat out told us what y prime is, right? So if all of this right here is y prime, we can simply integrate to find function y. All right, so we would say that y must be the integral of negative x squared over 3y dx. And hopefully you're looking at this with maybe a raised eyebrow, saying, wait a minute, what's wrong here, right? And hopefully you're noticing that something is wrong. And what is the issue is that we have an integral that has both an x term and a y term, right? If it were all y's, we could integrate with respect to y, or if it were all x's, we could integrate with respect to x. But like this, with them all mixed in, I don't know that we can do that. And you may think that this is sort of a wall that we're hitting, or this is a place where we just have to sort of stop and throw our hands up, but we don't, because we actually know how to handle this already. Because the way that we address this situation when we've got our variables all mixed up together like this, again, you've already been doing it this whole time. We just didn't necessarily know it. So what I would actually like to do is direct your attention back to example 2. And let's take a look at what we were actually doing when we solved this differential equation, what we were actually doing when we integrated. All right, and it's going to help, all right, if we take y prime and rewrite it as dy dx. So we had this, right? Now, how did we get from this expression in blue to this right here, right? Well, we said if the derivative of y is 6x, then y must be the antiderivative of 6x. But notice, when we went to undifferentiate, we had to add this dx term over here because we always need a dx in our integral, right? But where did that come from? It didn't just appear out of thin air, and it wasn't even one of those things where we were like, well, we know we need it, so we just put it in. No, it came from somewhere. And the answer is that it actually came from right here. All right, so what we actually did, without even really thinking about it, was this. We had dy dx equals 6x, and then we multiplied both sides of our equation by dx to obtain dy equals 6x dx. Okay, so now this is starting to look more like what we had right here, right? However, all right, we just had plain old y on the left-hand side, not dy. Well, again, what you did without even thinking about it was that you not just integrated the right-hand side, you integrated the left as well, right? We went from y prime to y. So what we did was undifferentiated both sides, right? Because of course, whatever you do to one side, you have to do to the other. We just hadn't really thought about it, right? And now you see where everything came from, right? What's the antiderivative of dy, or you could think of it as 1 dy? Well, that would be y. And then the right-hand side works out exactly the same as before, all right? This same method helped us out in example 2 as well. We had dy dx equals secant squared x. And so then, without even knowing it, we multiplied both sides by dx to obtain dy equals secant squared x dx, and then we integrated both sides to find y equals tan x plus c. So what we did here is actually called separation of variables. And you could probably see why it's called separation of variables, right? On this left-hand side, we had y's and x's. On the right-hand side, we just had x's, so we moved the dx over to the side with our x terms, so that we ended up with an expression that was strictly y's on one side, strictly x's on the other. All right, so let's come back to example 4 and see if this can help us at all. Hint, it will. All right, so let's apply this same methodology here. All right, currently we have dy dx equal to negative x squared over 3y. So let's begin by trying to separate our variables. All right, now remember, when you set up an integral, you always want your dx to be multiplied in, right? You want some expression in your integrand times dx, not divided by dx. So that kind of tells you which side your variables have to be on. All right, for example, if you notice the way we currently have our differential equation set up, dx is on the bottom, on the left-hand side. So guess what? I don't want my x's on the left. All right, I don't want a dx on the bottom. I want it on the top. So it looks like my x terms are going to be on the right and my y terms are going to be on the left. So from here, let's multiply both sides by dx. And we'll get dy equals negative x squared over 3y times dx. And we're very close now, right? From here, we just want to bring the 3y over to the left-hand side, so it's with all the other y terms. So let's multiply both sides by 3y, and that will give us 3y dy equals negative x squared dx. And some things don't matter, all right? For example, it doesn't matter which side the negative is on. It doesn't matter which side the 3 is on, just so long as your variables are separated, okay? So in this case, there's more than one way to skin a cat, as they say. All right, so now from here, let's solve, all right? And that means taking the antiderivative of both sides. So here we go. And notice how everything is all lovely and set up for us. We have a dy in our integrand on the left and a dx in our integrand on the right. If that weren't there, something should strike you as off because you need that to integrate. And again, it can't just come out of thin air. All right, so anyway, when we integrate the left-hand side, well, the 3 is just a scalar, and then the antiderivative of y is y squared over 2. And then on the right-hand side, the antiderivative of negative x squared will be negative x cubed over 3. Now, I've deliberately glossed over some things in previous examples, and I want to address that now. All right, obviously, anytime we take an antiderivative, we need to add a constant of integration, and I've just been putting it over here, all right, with the x's, right, plus c. That's what we're used to. But technically, all right, there is a constant on the left-hand side as well. When I take the antiderivative of 3y, all right, I get 3y squared over 2 plus some other constant, all right? So maybe I'll say plus c1 on this side and c2 on this side, but don't fret because there's an easy way to handle this, all right? At the end of the day, it really shouldn't matter, right? Whether I say plus c1 on the left and plus c2 on the right, or just plus something on one side of the equation. Let me show you what I mean. All right, so let's suppose in this particular example that c1 happened to be, I don't know, 4, and c2 happened to be, I don't know, we'll call it 7. All right, so right now we're actually working with 3y squared over 2 plus 4. Again, this is just hypothetical. There's no way we could know this right now. All right, plus 7. So let's suppose that that's what it was, that those were the constants of integration on each side. Well, I could very easily just subtract 4 from both sides, right? And then say 3y squared over 2 equals negative x cubed over 3 plus 3. And oh, look, right? What am I left with? Just one single constant on the right. Or I could move that 3 over to the left and say 3y squared over 2 minus 3 equals x cubed over 3. So instead of handling each constant separately on each side, you can just say plus some big super constant on either side of the equation. And the hint is that it's going to be easier to put it with the x's. All right, so let's do that from here. I'm just going to section this off, okay? So for right now, we'll decide that we have 3y squared over 2 equals negative x cubed over 3 plus one big super constant, right? We just combined all our constants onto one side of the equation. All right, well now we want to solve for y, if we can. And here we can, so we will. All right, so first things first, y squared is being multiplied by 3/2. So I will divide by 3/2 by multiplying both sides by 2/3. So times 2/3 on both sides will leave me with just y squared on the left, and then 2/3 times negative x cubed over 3 plus 2/3 times c. Okay? And then when we simplify, y squared equals, we'll call that negative 2/9 x cubed plus, now look, at the end of the day, you can say plus 2/3 c, or you can recognize that 2/3 times a constant is just another constant. So you can just say, again, plus c. Some people like to call this new thing c1 because technically it's a different value than the previous value of c. I'm not that nitpicky though. Constant's just a constant. That's good enough for me. All right, so I just leave it as another c. Okay, and then to solve for y, you'll just square root both sides. So you'll get y equals the square root plus or minus, of course, right? And then you can say negative 2/9 x cubed plus c, and yes, it is important that that c is under the radical, right? We know that we cannot split this radical up. We can't just say, oh, square root the first term plus square root of c. Nope, not a property of radicals. But there we go. We've solved. And it wasn't too bad now, was it? All right, so now that we are comfortable, maybe, with the idea of separating variables, let's practice some more on the next page. Okay, so we've been using this technique called separation of variables, and guess what? It is only useful on what we call separable differential equations, which means it is possible to collect all your x terms on one side, all your y terms on the other. Not every differential equation will be separable. Fortunately, we only cover separable differential equations in this course, so if you can't separate it, you can't solve it, at least right now. One day maybe you'll take a whole class in differential equations and you'll learn all the fancy techniques, but for now we just focus on separable. So let's start practicing our separation of variables in example 5. Alrighty, so we have y prime equal to this expression in terms of x's and y's, and now we know that that's really not a big deal. Alright, but to solve, it will first definitely be helpful for us to rewrite y prime as dy dx. And now again, I don't want a dx on the bottom, right, or a dy on the bottom, so it looks like my y terms are going to have to be on the left and my x terms will have to be on the right. This won't always be the case. It'll mostly be the case. All right, so now I'm going to simply multiply both sides by dx. All right, so we'll do dy equals x squared minus 3 over 6y squared times dx. And then I'll multiply both sides by 6y squared to bring all the y terms onto the left. So I'll end up with 6y squared dy equals x squared minus 3, technically we want this in parentheses, dx. Yay, my variables are separated. That means I'm good to go ahead and integrate both sides so that we can solve for y. And when we do that, all right, well, the integral of 6y squared dy, that's just going to give us, let's see, 6y cubed over 3. Again, plus c, but I'm just going to leave the plus c for the other side. All right, so equals, and then the antiderivative of x squared minus 3 is going to be x cubed over 3 minus 3x, and then I'll throw the c, one big c, onto the right-hand side to scoop up both constants of integration. Okay, now, let's simplify this before we start messing with it. So this just leaves us with 2y cubed equals x cubed over 3 minus 3x plus c. And then when we go ahead to solve for y, the first thing that we will do is divide everybody by 2. Y cubed equals x cubed over 6 minus 3x over 2. And then technically it's plus c over 2, but some constant divided by 2 is just a constant, so I'm just going to leave it as a c. And then the last thing to do, of course, is cube root both sides. So function y equals the cube root of x cubed over 6 minus 3x over 2 plus c. Again, that c needs to be inside the radical. All right, done and done. Example 6. Oh, this is getting fun now. So yeah, it can look a little confusing when you see y prime, but that just means 12 times y prime. All right, so let's rewrite this with y prime written as dy dx, right? And there's actually not much that we need to do here, right? The only thing that's preventing us from having everything completely separated is the dx on the left, so we'll just multiply both sides by dx, and that will be it. So we'll have 12y dy equals 7e to the x dx. And we're good to go ahead and integrate. So here we go. Integrate both sides. 12y integrates to 12y squared over 2 plus c, but I'm going to move that over to the right later anyway. And then 7e to the x integrates to 7e to the x, and then there's my plus c. We'll simplify the left to get 6y squared equals 7e to the x plus c. We will divide both sides by 6 to leave us with y squared equals 7/6 e to the x, well, plus c over 6, so plus c. And then, last but not least, to solve for y, we will square root both sides, which leaves us with y equals plus or minus the square root of 7/6 e to the x plus c. Great. Okay, now in example 7, this is where things are going to start to get interesting. Not in terms of the calculus, actually more in terms of the algebra. So look alive. Alrighty, but all the calc stuff is the same. All the ideas are the same. All right, so let's see what we got so far. Alrighty, we've got, let's see, x squared plus 4 dy dx, it's already written as a fraction for us, equals xy. Okay, and since dy is in the numerator on the left, I'm going to want my y terms on the left. So first things first, let's multiply both sides by dx, which will leave me with x squared plus 4 dy equals xy dx. Okay, now, yeah, you have a choice. Maybe I'll divide both sides by y first to move that y on the right over to the left, which gives me x squared plus 4 dy over y equals x dx. And then, last but not least, we'll divide both sides by the quantity x squared plus 4 to have all of our x's on the right. So we will have dy over y equals x over x squared plus 4 dx. Okay, we are completely separated in terms of our variables, so we can go ahead and integrate both sides. Here we go. All right, now the antiderivative of dy over y. Well, that would be the natural log of y, right? And then on the right-hand side, this is going to be a pretty straightforward u sub with u equal to x squared plus 4. I'm not going to go through it. I'm going to assume that you can do a u sub at this point. So when you do that, you will get 1/2 times the natural log of x squared plus 4 plus c. Again, need my constant of integration for both sides. All right, now this is great. I have what the natural log of y is equal to, but I'm not so interested in that. I want to know what y is equal to. All right, so I think, all right, how am I going to undo the natural log on y? All right, well, the answer is exponentials, right? Exponentials and natural log are inverses of one another. All right, so I am going to put each side of the equation in the exponent of e. I'm going to exponentiate both sides. So that looks like this. E to the natural log of y equals e to the everything on the right-hand side, right? So it's basically e to the left equals e to the right. Notice, even that plus c is up in the exponent. Okay, and now what's the whole point of even doing this? Well, so that the e and the natural log cancel one another out. And on the left-hand side, we're good to go, right? E to the ln y, e to the exponent of e that gives me y, right? Well, these just sort of annihilate each other, and I'm left with y equals, and then everything on the right. Now you'll notice I haven't canceled out the e and the natural log on the right-hand side, and that's because I can't yet. All right, the way I like to think of it is that you cannot cancel them out until they are in direct contact with one another, right? So like over here, it was just e to the natural log uninterrupted, whereas on the right, I have e to the, this 1/2 in the way. Okay, so we need to fix that. All right, we need to get that 1/2 out of the picture so that the e and the natural log directly cancel. And if you remember your exponent rules, right, you might remember a little trick that says something like this, right? If you have the natural log of, you could phrase this however you want, right, a to the n, that's equivalent to n times the natural log of a. In other words, exponents that are inside a natural log can come down in front as multiplication and vice versa. So if I'm seeing this 1/2 down in front as multiplication, that was probably up here in the exponent previously. So let's put it there, get it out of the way. And we'll have e to the natural log of x squared plus 4 to the 1/2 plus c. And then, of course, anything raised to the 1/2 means it's just being square rooted. So let's write it like that. Square root of x squared plus 4 plus c. Now, you may think, right? Oh, I am in direct contact with the natural log. They can just cancel out. But what's preventing me from doing it? The culprit is actually this plus c right here, right? It's not just e to the natural log of stuff. It's e to the natural log of some things, and then some other stuff that's not in the natural log. That plus c is not in the natural log. If I had this, I could go ahead and just cancel the e in the natural log. But unfortunately, I do not have that, so I can't. All right, I need to get this plus c out of the way now. And again, exponent rules are going to help us. All right, we have a property of exponents, right, that says if I am multiplying two like bases, right, x to the a times x to the b, that is the same thing as keeping the base and adding their exponents. So there's no reason why I can't work this in the other direction. For example, if I had x to the 7th, I could say, oh, well, that is x to the 4 plus 3, and then rewrite that as x to the 4th times x to the 3rd, right? So I have to go from the sum of the exponents to a product of two like bases with those exponents. And that's exactly what we're going to do down here. I have a sum of exponents, so I am going to go from a single base with a sum of exponents to two like bases, each with those exponents, right? So e to the natural log x squared plus root x squared plus 4 times e to the c. Now we're good to go ahead and cancel the e with the natural log. And that leaves us with y equals root x squared plus 4 times e to the c, right? Notice there was no natural log with this term here, so there's nothing that's going to cancel. E to the c is just e to the c. However, e is just a constant, right? 2.718281828, yada, 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 to a constant. So any constant raised to a constant exponent is, you guessed it, going to be a constant. So we can reduce this even further to root x squared plus 4 times c. Notice the c is on the outside of the radical now, and I think a nice sort of presentable way to leave this is y equals c times root x squared plus 4. And that's done. So now the difficult part of this was not the separation of variables. It was not the integration. It was the sort of algebra pre-calc kind of stuff about how to manipulate the natural logs and the exponents. So you might want to take another look through this example because this comes up all the time. It's not one of those things where it's like, oh, but how often will you see it? Because the answer is all the time. You'll see it all the time. Okay, and I'll make sure that we get some additional practice with this, I think, on the next page. Let's go ahead and see. All right, and all this does now is bring us to finding general solutions and then also obtaining particular solutions, which is very simple, as you saw in the previous video. So find the particular solution to the differential equation. Wow, that looks pretty gnarly. Don't worry, it's not. And that will pass through the point 0, 1. So let's go ahead and first get the general solution, then we'll find the particular solution. So here the dy and the dx are actually already separated. So now we just need to get everybody on their appropriate side. And here's the case, since the dy and the dx are both already in the numerator, it doesn't matter what side you put either one on. I imagine we're more comfortable with y's on the left and x's on the right, so we'll leave it that way. And all right, so let's move this term over to the right-hand side. So that will give us e to the negative x squared times all of this business over here equals negative xy dx. Okay. So we've established which side is the y side, which is the x side, and now let's just move everybody to the appropriate location. So I'm going to sort of one-shot this. I'm going to divide both sides by y to move him over to the left, and I will divide both sides by e to the negative x squared to move that over to the right. So when I do that, I will get y squared minus 1 dy over y equals negative x over e to the negative x squared dx. Okay, variables are separated. Let's integrate. Now, before I integrate, the left-hand side, right, you might be thinking, oh gosh, y squared minus 1 dy over y, okay, maybe it's a u sub, yada, yada, yada. No, right? Remember, this is an STD. In fact, let's write it just because that's fun, right? Use that to your advantage. Simplify this before you go to integrate it. It'll make your life easy. So when you divide each term in the numerator through by y, you'll get y minus 1 over y dy equals, and then on the right-hand side, okay, well actually maybe it would be helpful, instead of negative x over e to the negative x squared, let's bring the e to the negative x squared up into the numerator so that we're left with negative x e to the positive x squared dx. That's going to be a little bit easier to handle. Okay, so let's integrate both sides. The antiderivative of y will be y squared over 2. The antiderivative of 1 over y is natural log y. And then on the right, this expression on the right can easily be handled with a u substitution, with u equal to x squared. And when you do that, you would get negative 1/2 e to the x squared and then plus c. All right, now, normally we've been going about our business and solving for y explicitly, but if you look at what we have on the left-hand side, the y squared and the natural log of y, you're not going to be able to do that. All right, and that's fine. So we can't solve for y explicitly, so we're just going to leave it, okay? But we do still need to address the whole particular solution thing, okay? And we need to ensure that our curve will pass through the point 0, 1, so that when x is 0, y is 1. So let's make those substitutions to get our particular solution. So anywhere I see a y, I'm going to put a 1, right? So minus ln 1 equals, and then negative 1/2 e to the 0 plus c. All right, so 1 squared over 2 is 1/2. The natural log of 1 is 0. And then on the right, I'll have negative 1/2 e to the 0 is 1 plus c, which leaves me with 1/2 on the left equals negative 1/2 plus c, so that when I solve for c, I get that c equals 1. Therefore, my particular solution to the differential equation is y squared over 2 minus ln y equals negative 1/2 e to the x squared plus 1 for c. Done and done. All right, let's move on to example 9, which looks a little intimidating, is not very intimidating. The only question you might have is, which is my y and which is my x? The fact that the p is capitalized, sort of clues us in that that's probably the y. Also, t is typically used as an independent variable, but if there were any doubt, this initial condition right here should seal the deal for you, right? P of 0, oh, okay, so p is our dependent variable. All right, so let's just rewrite this. The variables are already separated. We're going to assume that k is constant because we have not been told anything to the contrary. All right. And so now, it's actually just going to be easiest, I think, for me to move the dp over to the right. So when I do that, I will have k times p minus 70 dt equals negative dp. And then Now, where you want to keep the k is up to you. Doesn't matter, all right? I'm just going to leave it on the left. So for now, I will just divide both sides by the quantity p minus 70, which will leave me with k dt equals negative dp over p minus 70. And you don't have to do this. This is just sort of an aesthetic choice on my part. I'm going to move the negative over to the left-hand side. And that's just because since p is like my y, I kind of want to keep as much away from it as possible. But again, you don't have to. So I'm just going to say negative k dt equals dp over p minus 70. Okay, now we can go ahead and integrate both sides. My variables have been sufficiently separated. So integrate the left, integrate the right. The antiderivative of negative k dt, well, the negative and the k are both just constants. So that will just integrate to negative k t. I'll put my plus c on this side since this side is like my x side and the right is like my y. Okay, and then on the right, I will integrate dp over p minus 70. Maybe you can see this without having to do anything formal, but if you don't, again, this is just an easy u sub with u equal to p minus 70. Okay, and when you do that, you will get the natural log of p minus 70, and we're going to keep all our c's on the left there. Okay, so that's great. I know what the natural log of p minus 70 is, but I want to solve for p. Okay, and maybe at this point it's going to be easier for you just visually to move everything around like this. This is sort of how we're used to having things. Okay, so let's go ahead and solve for p. And again, well, the p is stuck in a natural log. What is going to help us with that? Exponentials, right? We're going to exponentiate both sides, which means that we do e to the entire left-hand side equals e to the entire right-hand side. Okay, so now if we look on the left-hand side, there's nothing preventing us from canceling the e and the natural log, nothing in the way. All right, so we'll do that, and we'll be left with p minus 70. And then on the right, there's nothing to cancel because there's no natural log on the right. So we're just going to leave it as e to the negative kt plus c. All right, and you could actually leave the right-hand side like that, but more often than not, they're going to do what we had done previously and separate the exponents into the exponents of two like bases, right? So meaning this, right? Saying that e to the negative kt plus c is equivalent to e to the negative kt times e to the c. And then of course we'll go one step further and say that e to any constant is also just a constant itself, right? So times c. Okay, and you know what? I'm probably a little bit more comfortable with that c out in front. So ce to the negative kt. And then last but not least, to solve for p, I'm just going to add 70 to both sides. So ce to the negative kt plus 70. And now all we need to do is address this particular solution part. Now, when we solve for a particular solution, we're only going to be solving for this c here, right? That's all we can solve for, right? The constant that came from integration. The k, we can't worry about. That was, given in the problem. We have to let it go. All right, and it's actually not even going to matter anyway. All right, so let's take a look at our initial condition. It said p of 0 is 140. So when t is 0, p is 140. All right, so let's go ahead and set that up. And we'll just sort of section this off right here. All right, so p is 140, when t is 0. So e to the negative k times 0 plus 70. All right. And then 140 equals c e to the 0 plus 70. And e to the 0 is just 1. So currently we are at 140 equals c plus 70. And so then we see that c is just equal to 70. So that would make our particular solution to the differential equation, I'm going to have to come down here to write it, p equals 70 e to the negative kt plus 70. Okay, so that's it. If you can do everything that we've done together in this packet, you are more than good for separation of variables. But of course, you're going to want to practice suggested exercises. Give them a go. Later.